Hi, this is Rahul. In this lecture, I'm going to talk about heap. Why I'm going to talk about heap? Because heap data structure is very useful if we are going to learn the graph algorithms. In Prim's algorithms, we use max heap or min heap, and in Discrete algorithms, we use min heap. So, if we are learning the graph algorithms, then if you don't know heap, that would becomes very difficult to understand a time complexity analysis. In time complexity analysis perspective, we should have knowledge of heap. How do we actually we build the heap? How do we insert in heap any elements? How do we delete any element from the heap? So there are some very interesting properties of heap, so that's why this heap data structure is very useful for any time complexity analysis of graph algorithms. So we look at a heap first. Suppose we have binary tree. You can see over here that we have a binary tree, 16, 14, 18, and these are the elements which are filled in this binary tree. And you can see level at levels how many elements we have. One elements, and level 1 we have two elements, level 2 we have four elements. How these numbers are increasing of two of levels, number of levels. So if we talk about level 2, number of elements which are present in this level, 2 power 2, at number level 2 to power 1. This is how we are feeling. Now if we talk about heap, this is just a binary heap, but something different. What is different? At each level, we fill element from left to right, right? Once the previous level has been filled, we will move to the next level. So, what we see here, you can see this level has completely filled of 2 power 2 elements because level is 2. And what we see, if there is the incomplete levels, that would be only the last one, right? Level 3, you can see this level can be incomplete, and the previous level must be filled, completely filled. Then if I ask you the how many is elements maximum which can be present in this level, 2 power 3, you can say, right? Another very interesting thing, so which is very useful, the very important one, the height of this tree. We always get the height of this tree of log n. N is what? Number of element in this heap or this binary tree. If I ask you, how do we actually find out the number of element at each level? The formula you tell me in form of height. What do you, how do we actually, you tell me? So n, the formula would becomes n by 2 power h plus 1. N is what? Number of element. H is what? Height. So at this, so height of element, height of subtree of this one becomes 0. Why? Because it doesn't have any child, so that's why height is 0. If we talk about height of this root, is it is 3. This is how we actually figure out what is the height, and with the help of height we compute the number of elements present at each level, right? So this is how we actually filter. These are the rules I have told you just now, and we will move forward. Two things. There are two type of heaps: max heap and min heap. So what are the properties we have? So max heap, the parent of child. So see, this is the parent, and we have two childs of this parent, and the parent must be greater than or equal to of these two child. So if max of child we take, we find, and parent must be greater than or equal to of these two, then it is the max if. It will hold for all the parent and child which are present in this heap. So this is the max if if we talk about mean if parent must be greater than, less than or equal to minimum of its child. We have only two child, so that's why I have written only child 1 and child 2. Now the storing of this heap is very interesting one, very easiest one. So this is why we use the heap or min or max if. So how do we actually store this heap in an array? So you can see 16. I have written number over here: 1, 2, 3, 4, 5, 5, 6, 7, 8 numbers. These are locations I have written. So and are you able to relate these two numbers and these two numbers? You can see these two numbers are just becoming doubling from the previous one, 1 to 2 and 2 to 4 and 4. But the next child of this one, and next child of this one, and next child of this one, how many? This is next one. 4 plus 1 5, and 2 plus 1 3, and 6 plus 1 7, and right child always be the next location of the left child. So if you are able to compute the next left child, so it is just double of parent locations. And then if you do plus 1, then would become the location of right child. I hope this is clear. So I have written here locations, and you can see how these elements are filled corresponding to locations. It is very simple. So, right, if you can assume that there are links, some link with this one. This is very interesting. So you must have just an array and not need to make this binary heap. You can assume there are links with when you compute this one 2i. You understand of you understand this is the first left child, and 2i plus 1 if you it is I is a parent, then it is a right child. This is how you compute. So I have taken, so I where I is equal to 1 and left child is this one. I hope this is clear. Now we will to see one more thing. So if you are given the location of child, can you figure out what is the location of parent? Yes, you can do it. Why? Because you see here the location of child is just doubling, and you have location of child, you can find out the location of parent by just making half of. You can see, if you do half of this one, suppose you have ith location, and find out this child location, sorry, parent location. Now you do 7 by 2 and take floor, and you get 3 numbers. Yeah, I think this is clear. The advantage of this making heap, what we do if we want to find min or max element from the heap or from the array, that would becomes the time complexity, we get only one, right? The searchings of any element from this heap, we will only spend log n time, right? So the deletion and insertion rate, disadvantage of this one is deletion and insertion also will take a log n, because we have to maintain the property of heap. So that is the reason. Now we'll see one more things, which is very interesting. How do we actually build this main max if or min if? In this examples, we will look at only the max if here. Now you can see we have an array. The array having the same element as we had in the pictures we have seen, and you can see we have 4 5 3 6 and all these elements. And the beginnings, what we do simply from the first, we have taken this 4 elements and we have made this like this. This is just the we just assumptions on pictures, how do we actually the heap is built of. But and while we're doing programming, so will have only this many this only array, and we don't have any things like this in linked list kind of things. We This is just an assumption, and for understanding, so I'm making this big pictures. Now you can see over here, so once one has come, so you had added one. So you can see max if max if property is what? Parent must be greater than or equal to its a kid, child or kid, so that it is holding it. So at 3, when we have added 3, you can see 3 is still holding the properties, because 4 is still greater than or equal to both childs. Now when we add 2, what we say, 2 is 2 has as we have seen, the once the previous levels has filled up, then we will start from left to right, right? So what we have added here 2, and what we see, this 2 is less than of its parent, sorry, greater than of its balance. What is it? It's violating the max heap property. So the what we do, we simply swap it out. You can see 2 is swapped with 1, so what we got, 2 1 is here and 2 is again. We check because this value was changed, so that's why we have to check next one. If it has changed, then if it is changed, then we, if it is available, so for it is correct one, 4 is 4 variant is greater than or 2, so we don't change. Now we'll next add the 16 here. So you can see over here 16 we have added. 16 is a child of 2 and 16 is greater than of 2. What we do, simply swap it. You can see we have swapped, and 16 is still is a child of 4 and greater than of 4. What we do, simply swap it out. So this is how if we recursively follow this process, what we get, the build, max if resultant max if we get this type of max if. So all these things. So how do we actually write the algorithms, we'll see. So in the beginnings you have just array, and we do swapping in this array only, and we assume that this is a max if. So how do we actually do it? Suppose we have a number of elements in this array, a size, a dot size. I am taking the number of elements, and I will start from a by 2. Why I am starting? Because the parents would be present of leaf nodes at a size by 2. Why it is so? So if I am taking number 10, 10 by 2 is what? 5. So this is the last parent which is having at least one element. So you can see over here, this is one. So we will move from this tree, then next tree, next tree, next tree, and next tree. This is how I do process the tree, sub trees, and make the heap. So in the beginnings we have these many elements. As the elements present in area, I have made this for one. I hope this is clear. Now you can see I have written all the roots we have in this subtrace. So a4 we have a4 we have, a3 we have, and a2 we have, a1 we have, and we process all the we process all these sub trees with the help of these roots. And what we see, we have these these subtrees root a5, a4, a3, a2, and we one by one we pass all these roots to this maxi function. And similarly same times we pass also the array as well. Now we first compute the index of left child, index of right child. As we were doing, 2 into p would become the left child, and 2 into p plus 1, that would be the right child. Now we'll take these examples. You can see over here, for these examples we process this max heapify, right? So largest I will consider the parent what we are passing. Suppose 2 for 2, the index of 2 is p, and we are passing this. I am considering this is the largest one. Take, this is the largest one. Now what we do in the first step, what we do, simply just check the size of left child, or left child is within the index of array. If it is index the array, if next we again check if it is greater than of parent. If it is the greater than of parent, what we do, we update the largest. What we see in this example, 2 and 10 is compared, and what we found, 2 10 is greater than, then we update this as the largest one. This would become the largest one. We did from this line, right? Now Next step, what we do? We again check the same things. Right child index is falling within the array size, and right child is greater than this largest one. If this is left child, right child is this largest one, we update it. What we see? 10 is 20 is greater than this one. Right child is also greater than largest one, which is pointing out. So largest would become next step 20. Sorry, this R index. So largest is pointing right now this 20. Now what we had, well, what will have largest it not remain the same as we did in this step. So what it means, so we will save this largest with parent. So 20 will be saved with this one. So it will becomes so that the heap will becomes 20 and 10 and 2, right? I hope this is clear. Now what we see here, we have changed these numbers from 20 to 2. What that means, the heap properties might be changed here. So what we do, see the largest elements was this one, it was pointing out. So largest one will be again callbacks. We call back again. For this row we maintain the heap properties because we have changed these elements. Why we do not call for this one? Because this is the maximum ones, and we will later on checks from this next the parent of this ones to of property of maxif of this one. So we will call uh, to subtree this one and check again is there any changes. If there has been changes or need to update, we will update it now. So let's compute the time complexity, which is very important. That is what we are learning, the build maxif. So here we are just only considering maxif only. So that is so we will pass, as I told you, we from a by 2 is a size by 2 to 1, and you can see time complexity is n, and callings this each elements order of log n. So the time complexity of maxif is log n because we are going to up to height only. So the time complexity of this is order 1, and the trees or levels we are making, that is on log n's. Just this function is calling and again the height we are making. So the time complexity of that only height of. So that is the reason I have written log n's and n log n. So the time. So are you thinking the time complexity is n log n? If you are thinking, then you are wrong. I'll prove it here. So number of elements, let's count it. And the height of this tree from 0 to 3, you can see over here. And if you want to compute number of element at each level, so that would become size. I told you in the beginning of this lecture, 2 power height is 3, 2 power 3 plus 1. Number of elements at this element, you that would become 10 by 2 power 10. Number of elements in this array, we have 10 by 2 power 3 plus 1. That would becomes, we take seal of these numbers, 10 by 2 16, and that would become ones. This is how we compute the number of elements. And let's say we have number of elements, we are calling the maxify each times from here to here. Let's do it. And so number of elements at each level, this is, you can see maxify we are calling, right? This is what I have written same things as I told you. Now number of elements we have, you can look at this function. This is this is nothing, just summation of h barabar 0 to h is equal to log n, the height of the tree. So you can see this is what number of element at each level, where h is what height of the subtrees, right? And we will multiply with h. H is what the time complexity of maxify. See, as we are doing here, see, n is what number of element at each levels and log n. So I am assuming here n, but it is not like that. So and at each levels we have n by 2 power h plus 1 into log n. And I have taken integrations. Integration is just doing the same things as we see in summations. We do log n times, and I replace this one by h because we are taking multiplication, we are computing for h. So we take n outside, you can see, and just take integration of this one, we get this value, and if we compute this one we get constant one. If you don't know, then you can remember it, and you can have uh, geometrical progression. So that's why we get the progression of this one h plus 1. If h goes to infinity, then this value goes to 1. So that is the reason, and we get this n into c time complexity. If you are computing summations, then then that case also we get constant, and this case also we get constant. So n into constant we get order of n. This would look like very any magic happens. The time complexity is whole, not n log n. This is order of n only. This is very interesting. So the one more things you might have heard of a priority queue. Priority queue just nothing. The priority queue uses the data structure of main or max shifts, and provide you functionality like increase k, decrease k, or insert k, all those. This is abstract data types. This is nothing to be learned. If you know the max shift min shifts, that is very easy to you can make the functions like increase k or decrease k, or minimum k, all those things, min or max priority queue you can build of yourself. If you think this lecture is helpful, or if you have any confusions, you can comment in comment sections. I will answer you if you feel it is helpful for you, and you can share with your friend. That will motivate me to make you quality lectures like time complexity of algorithms. Thank you for watching.